The second page of the worksheet from section 5.2 has a number of algorithms for counting that are actually incorrect. And these examples of incorrect algorithms come from student work that I've gotten in the past. So in each case, I wanted to talk through the way you can tell that there's something wrong with the algorithm. And the thing you're looking for is something where either in the steps themselves, perhaps not every possibility is being generated, or sometimes more than, each possibility is generated more than once if we're not careful about the way we fill them in. And then the second error you can look for is when you count the number of ways to do each step, sometimes it's easy to talk yourself into a certain number when really it could be that the answer to the number of ways for that step may be dependent on something. So those are the two things to look for. So for example, if we're trying to answer the question about the number of ways to deal 5 cards where the first card has the same value as the last card. So for example, if the first blank has an ace in it and the last blank has an ace in it, then that's what we would count. So we can trace through the algorithm by actually following the steps. So step 1 here is fill in the leftmost card. So let me do that. So let's say the first card is an ace of spades. And indeed there are 52 choices for what I could have used there. Fill in the next card. There are 51 different ways because the next one has to be a different card. So maybe the 2 of clubs would be second. And indeed there are 51 ways to do that. It could be anything but the first card. Perhaps the 7 of hearts is the third card. And again, the 50 ways that's correct. And maybe the next card is the King of Diamonds, which was one of 49 ways. And then it's the last step here that causes the problem. Fill in the rightmost card, and we have to have the last card match the value of the first card. So the last card would be forced to be something like the ace of diamonds. It has to be one of the 3 other aces. So if I put an ace here, then I've got 3 other choices for what to put an ace there. Of course, the problem is, if I put a different set of then that last choice would not have only been in 3 ways. So for example, if my first choice was ace of spades, my second choice was 2 of clubs, my third choice was ace of hearts, and my fourth choice was king of diamonds, now when I get to this point, there are only 2 options for what can go here. It still has to be an ace, but there are only 2 available. And similarly, I could have more aces in here, and in fact I could accidentally pick 4 aces as my first 4 things, and I'd have no choices for what goes there. So this algorithm has a problem in that you don't always have 5 choices. It may be that you already have used all your aces, but certainly even if you do get through all the choices, the 3 is not the correct number of ways because it depends on what happens before that. So this algorithm could actually be fixed. This one's not fatally wrong. We talked about in class the fact that you want to fill your blanks in order of most restricted to least restricted, and so if you renumbered step 5 as step 1.5, in other words, move it up here between step 1 and 2, so that you fill in the leftmost card first, and then fill in the rightmost card, and then fill in the other 3. These numbers will change a bit, but then you should have no trouble with the multiplication principle. Okay, let's talk through this one. We have an algorithm that's supposed to be counting the number of combination locks, which are supposed to be an ordered list of length 3, so filling in 3 blanks. And the numbers have to come from 1 to 50. You have to have exactly 2 matching numbers. So, for example, if I follow the algorithm that's here, fill in the left number, maybe the left number is a 7. Fill in the center number to match the first, so there's no choice there, I only have one way of doing that. And then fill in the rightmost number to be anything that's different, so maybe 20. So 7, 7, 20 would be a legitimate combination lock. It's an order list of length 3 with entries from here and having exactly 2 matching numbers. So if I do that in all ways, 50 times 1 times 49 will in fact count the number of combinations that look like that. But this doesn't count everything that I want. I could have the matching two numbers anywhere in the combination, does not have to be in the first two spaces. So therefore, even though these are all correct, 50 times 49 is the number of ones that look like this, there are other possibilities. You could have the first and third position match, or you could have the second and third position match. So really, if you broke the problem into three cases, one case for each of the pairs of positions that would match, first and third, first and second and third, then each of those answers would be 50 times 49, and you would be able to add those together to get the correct total number. But this algorithm is wrong only because it's incomplete. It counts legitimate combinations, but it doesn't count every possibility. In the last example, we're supposed to be counting 4-digit numbers with at least one 7-digit. And so we can say, let's choose one of the 4 blanks where we're going to put a 7. So maybe I'll make a little X there for what one I'm picking. So there's 4 choices for which one of those that I pick, and I'll put a 7 in there. Fill in the first non-empty blank with 0 to 9, so I can put a 5 here. Fill in the second non-empty blank with anything, put a 0 there, and a 0 there. So this would be correctly following the 3 steps. Pick where the 7 goes and then fill the other 3 numbers. But this has more than one problem. First of all, with a 4-digit number, we're allowing a 0 to go there according to this algorithm. And we don't really want to have a 0 there if it's really going to be technically a 4-digit number. But that's a small matter. In fact, you could interpret a 4-digit number as something that starts with a 0, so maybe that's not even really a problem. The bigger problem is that of the ones that you're supposed to count, you're actually going to be counting several of them more than once. And you can see that by thinking about applying the 4-step algorithm where you make different decisions, but you end up with the same answer in the end. So for example, if I, instead of picking the 7 here, and then let's say I put a 5 there, a 0 there, and let's say I put a 7 there. So that's following the same 3 steps. Decide where the 7 goes, pick anything for the first blank, I put a 5, pick anything for the second blank, I put a 0, and pick anything for the third blank, I put another 7. If instead I had said that in my first step, where it says choose one of the blanks to get a 7, if I had marked this one off, and then chosen a 5 for the first non-empty blank, a 7, a 5 for the first non-empty blank, a 7 for the next non-empty blank, and a 0 for the next non-empty blank. That's really a different decision in each of these 3 steps. In fact, it was a different decision in step 1. It was the same decision in step 2. I put a 5 there. In step 3, here I picked a 0, here I picked a 7. In step 4, here I picked a 7, here I picked a 0. So it really was a different combination, a different path of decisions through these steps, but one led me to this answer and one led me to this answer. So this particular string of 4 digits is counted twice, depending on which sequence of choices you made. And so that's bad. So that means that the number we get here will actually be too big. We'll count some of them twice. And if there was a number that had 3 7s in it that you built, then you'd be counting that much more than twice. And if you had picked all 4 7s, you're going to count that multiple times as well. So this one, part C, actually overcounts, even if you ignore the possible ambiguity about what we're doing with that first digit. B undercounts because we're not including all of the possibilities. And A, the error in A is actually in the counting itself. The steps are in an order where we're not able to answer the question about number of ways the same each time. In particular, that step has a problem with the analysis. So this is about every possible type of error that you can see in an algorithm. Hopefully by this video or by the written solutions to these problems, you will you'll sort of see what's wrong and avoid those common errors in your problems.